Standard C code executes one line at a time. Verilog is different. It executes instantaneously across the entire design. Verilog uses a text-based syntax to define and map concurrent electrical reality. We interact with this code in two distinct phases. Simulation tests the temporal behavior of a design inside a software event queue, while synthesis physically stamps that code into a gate-level netlist. Junior engineers often struggle by applying sequential software logic to hardware. Writing Verilog as if it runs from the top down creates immediate race conditions and timing errors. Designing functional hardware requires abandoning software habits to understand the underlying mechanics of discrete event execution. The IEEE 1364-2005 event queue is the engine of the simulator. It dictates how the software processes hardware time. We can observe this engine by testing two blocks of logic that differ only by their assignment operator, a blocking equal sign versus a non-blocking arrow. A blocking assignment executes sequentially, collapsing logic into a single path. Conversely, non-blocking assignments use a two-step model. In the evaluation phase, all right-hand values are captured simultaneously. In the update phase, they deploy to left-hand targets, forming distinct, parallel physical flip-flops. Because of this mechanic, RTL Design relies on a strict rule: always use non-blocking assignments for clocked sequential logic. Respecting this two-step simulator mechanic prevents data collisions in the physical hardware. If the code is ambiguous, the synthesis compiler may default to creating an inferred latch, a component that traps data unpredictably. The legacy Verilog always block is susceptible to this. It forces the compiler to analyze event controls to guess if the designer intended to build combinational logic or a sequential register. Data types can be equally misleading. A variable declared as reg may synthesize as a simple wire. SystemVerilog introduces the logic data type to replace these legacy labels. The compiler infers its physical nature strictly from the context of its use. SystemVerilog also provides the always FF block. This functions as a technical mandate, commanding the synthesis tool to generate a physical flip-flop. If the code cannot generate a flip-flop, always FF interrupts the process with a strict error, rather than allowing the compiler to guess. These constructs shift the burden of hardware modeling from the compiler back to the engineer's explicit commands. Pipelining increases a system's clock frequency by trading cycles of latency for sustained throughput. We slice a long combinatorial logic path into segments by inserting sequential registers to bank data between clock cycles. This creates data dependencies. Routing a feedback loop backward across these registers delays the signal, clashing with incoming data. Relying on the two-step update of non-blocking assignments manages these temporal shifts, resynchronizing the data flow at each clock edge. Pipelining scales the simulation event queue's mechanics to the system level. Finite state machines pair a sequential state register with a combinatorial block that calculates the next state. Manually defining binary state codes with local param is a historical flaw that often introduces subtle human errors. SystemVerilog provides the type-def enum declaration, allowing for symbolic state definitions that the compiler maps cleanly. Clean synthesis requires the Van Hoffman coding style, which segregates sequential memory from combinatorial logic blocks. We isolate the state memory inside an always_FF block, using non-blocking assignments to advance the state. We then isolate the next state calculation inside an always_com block, using blocking assignments. This behavioral structure demonstrates the combinatorial side. The always block evaluates a selector state, routing inputs through a case statement instantaneously. Isolating state memory from transition logic creates predictable FSMs that synthesize exactly as they were simulated. A compiled silicon layout contains millions of gates operating concurrently across a physical landscape. An engineer navigates 3 layers of abstraction to reach this: the simulator event queue, the SystemVerilog syntax, and the final physical logic. Mastering non-blocking assignments remains the foundation for preventing temporal logic errors in this environment. Structures like always FF ensure that the engineer's intent is preserved without ambiguity during synthesis. The software syntax is a tool used to describe an underlying electrical reality. True RTL mastery occurs when the temporal behavior of the software simulation matches the physical constraints of the synthesized silicon.